Howdy folks, welcome back to Unit 7 for our AP review. And we're going to talk about sampling distributions today. So let's go ahead and jump right into it. First thing we got to cover is we need to be able to distinguish between what a parameter is and what a statistic is. So for us to do that, you need to know the difference kind of between, you have essentially your entire population here. So this is the entire population from which we're sampling. Maybe it's all North Pole High School seniors. Maybe it's all registered voters, but you have your entire population that you're interested in. And in that population, there are a bunch of things that describe that population. And that could be the population mean, indicated by mu, or the population median, right? Or maybe the total number of people in the population. Maybe we're talking about a census and we're trying to just count and we don't know. Okay, so parameters are things that describe the population, the entire population. And sometimes these things are, most of the time, these things are unattainable for us as statisticians or scientists. And there are many parameters that you can find, okay? There's the median, the mean, the total number, and also actually more importantly might be like the standard deviation or the variance of the population. Put a couple more dots. Those are all parameters as well. So anything that describes the population, the entire population. Okay, so statistics describe a subset of the population or the sample. So we're going to pull out, individuals or objects from the population, and we're going to try and say something about the population based on the sample that we've collected. And those statistics, what we might use to describe the population mean might be the sample mean, or maybe we would use the population or the sample median to try and take a guess at the population median. Now we definitely wouldn't use the sample size to try and guess the population size because sample is always smaller. But maybe for the standard deviation, we would use the sample standard deviation or the sample variance to guess the variance. So these are all statistics. These are all parameters. So let's create a sampling distribution. What we're going to do is create a sampling distribution using all possible samples from a population. So let's go ahead and choose a statistic. We're going to assume that we have the entire population in this case. And let's say that looks like this: 3, 5, 5, 6, and 8. And let's say this will be easy. The statistic of choice is the median. And we're going to take sample size 3. So every sampling distribution is basically it's every possible statistic from a given sample size from a population. So in order for us to talk about the sampling distribution of the sample median, we need to figure out what every possible sample is. So I'm going to start with 3 and I'm going to try and write them in order. Now this, you should be able to know how many there are before you begin. There are 5 things in our population. There are 5 different individuals here, and we are going to sample 3. So how many different combinations of 3 can we make from the total of 5? Well, you can go to your calculator and do 5 choose 3, choose notation, which will give you 10. So we know we need 10 results. So let's go through and grab groups of 3 and see what we can get. So that's 3. We could do 3, 5, and 5. We could do 3, 5, and 6. We could do 3, 5, and 6 again with the other 5. Okay, 3, 5, 5, 3, 5, 6, 3, 5, 6 again. We can do 3, 5, 8, and 3, 5, 8 with both 5s. And we could do 3, 6, 8. And I think that's all the ones that begin with 3. Now let's eliminate the 3 out of the group and see what other ones we could create. We could have 5, 5, 6. That's a different group. We could have 5, 5. Oh, I'm actually going to keep going down the list if you don't mind. So you could have 5, 5, 6, 5, 5, 8. 6, 5, 5, 8. And then you could have 5, 6, 8. And another 5, 6, 8. So 5, 6, 8, 5, 6, 8. I think that's all of the ones that we can do. That should be a total of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all of our possible samples. So here's all of our samples. This is all possible samples. Now the sampling distribution has to include all possible samples. Now let's talk about our sample medians. Let's go through and find the medians of all of the samples. Well, this one is 5, 5, 5, 5, 5, 6, 5, 5, 6, 6. So the sampling distribution of sample medians, oops, let's try that again. It's going to look like this. So 4, 5, 6, 7. It looks like there's 1, 2, 3, 4, 5, 6, 7 5s. And 1, 2, 3, 6. So that's what our sampling distribution looks like. Now this is a very small population, so we're getting kind of a little bit wonky of a sampling distribution, but this is what the sampling distribution of sample medians looks like. Now this is not going to look the same if I choose sample size 3 or 4 or sample size 2, for example. We would get a different result. So the sampling distribution is basically, if I were to take one sample of size 3 from this population, what can I expect my median to look like? And this tells us, right? It's going to be basically either 5 or 6 and probably 5. That's the sampling distribution. Okay, it says distinguish among the distribution of population, the distribution of the sample, and the sampling distribution of a statistic. So let's go ahead and take a look at this real fast. Yeah, so up here, this is our population. Okay, so we are, we can't sample the entire population most of the time because that would be too expensive. So instead, we pull a select number out. Okay, and so this is the distribution of our population. We can't afford to sample the whole population, so we pull a select number out. In this image right here, this is our sample distribution. In these two, this is our, if we do this over and over and over again, then we create the distribution of means. And this will get closer and closer and closer to the sampling distribution. Okay, so this is there you have your population, which is what you're selecting from. You have your sample, right? The distribution of your sample, which kind of resembles. And then if you take a mean of that sample, now we have two different. So this dot came from n equals 5, lowercase n equal 5. This came from lowercase n equals 25. So this right here is actually showing this mean, and there were another 5 dots that created this one. So basically, if you take a sample of size 5, and then you take a sample of size 25 and find their means, these were the means from those two samples. So this is our distribution of means, which ultimately will become our sampling distribution for x bar, because it says we're using the mean in both cases. Okay? Let's take a look. Determine if a statistic is an unbiased estimator of the population parameter. Okay, so in order to do that, we use kind of a controlled environment where we know what the population parameter is. We know that down here, let's take a look at the mean. Down here, the mean of this distribution seems to be somewhere around 16 or 17. And the median as well, it's perfectly symmetric, it's normal distribution. Here's our mean, and when we took, so our parameter of interest is the population mean right here. And here is our distribution of x bars down here. We have this distribution of x bars from sample size 10, and you can see that the sampling distribution for x bar is centered on the parameter that we're trying to estimate. And so this is unbiased. It's unbiased because the sampling distribution of x bar, or of the statistic, is centered on the parameter we're trying to estimate. Let's take a look at this one up here. This is the range. We used this before. If you're trying to estimate the population range with the sample range, it's not going to go well. Now it looks like these two marks are lined up on each other, but these are ranges. These are ranges. They're not the means. So the actual parameter of interest here is the highest value minus the lowest value. Well, that looks like it's about 30. So here is the population range. Does it appear that our sample, the mean of our sampling distribution down here, is centered? No, it's not centered at all. So this is extremely biased, right? If this were an unbiased estimator, then this center of our distribution should be over here, which it's not. So if we take a sample, we're going to consistently underestimate what the actual population range is. And that should make sense, because the only way that your population range is going to be, or your sample range is going to be the same as your population range, is if you have the highest and lowest value in your sample. And the likelihood of that happening is very, very slim. So you're more likely to get values that are like in here. You take the range, high minus low, and you plot your point. That's just how it goes. So this is extremely biased for estimating the population range. Describe the relationship between a sample size and the variability of the statistic. All right, this one's pretty simple. So hear me out. Let me make that a little larger. Yeah, so basically, if you're taking a sample of size 2, now if you'll notice here, when you take a sample of size 2, the mean, we took, I think, 10,000 for each. The mean of samples of size 2 is, so these are all averages, right? All the means of samples of size 2 from the population is still centered. It's still unbiased. It's still centered on the population parameter. However, we have a ton of variability, right? The mean is 16.01 here. It's very close. For sample size 25, it's still 16, so it's still taking a good guess. The problem is, if you're not taking 10,000 samples, you take one, and so if you don't want your one sample to be falling, your sample mean guess at the population mean to be falling way over here. You want it to fall as close as possible. So if you look at the standard deviation of the population, look at the standard deviation here, it's slightly less, but the standard deviation for 25, sample size 25, is much, much less. So, so as n increases, the variability of the sample statistic decreases. Yeah. You can see that the spread of this population is much, much smaller. So high N is good. The reason that's often unattainable is it costs money to do that if you're a researcher. You got to pay people to collect data. You got to pay people to be part of your study, so on and so forth. 7, calculate the mean and standard deviation of the sampling distribution of a sample proportion p hat and interpret the standard deviation. Okay, suppose you know that 17% of milk drinkers in Alaska prefer skim milk. You decide to take a random sample of, can you guys even see my head? Am I leaning back? Oh my gosh. I'm like Wilson from I'm like Wilson from Home Improvement. I'm sorry about that, guys. Holy cow. Okay, here we go. People probably don't even know what that show is anymore. Golly gee. So what is going to be the mean of my sampling distribution? So if I were to take a sample of size 15 from the population, and I were to do this for every single possible sample of size 15 from the state of Alaska, which is really, really large, we're trying to find what would be the mean of my sampling distribution. Where is that going to be centered? Well, it says it's going to be centered on whatever the proportion of milk drinkers that actually prefer skim milk, so it's kind of already given to us. So we know it's going to be centered on that. And so the next question is, what is the standard deviation of that? Well, the standard deviation is a little harder to calculate. You have to plug in 0.17 times 1 minus 0.17 divided by the size of your sample. And that should make sense because as sample size increases, we know that our variability decreases. So you put 15 under here, and let's go ahead and scroll on down. I've got my calculations done for me. If you want to try this on your own, feel free to pause the video at any time. Okay, so we're going to do 0.17 times 0.83 divided by 15, which will give us, when it's all said and done, about 0.0969. Okay, and our units here are, I guess it's just, this is proportion, so we'll just leave it unitless in this case. Okay? So what does this standard deviation mean? This means that we can expect a sample, I should say the mean of a sample. We can expect the mean of a sample except we're not doing mean here, are we? We can expect the proportion of skim milk drinkers from a sample of size 15 to vary from the actual proportion by about 0.0969 on average. Basically, if we were to go out and take a sample of size 15, it's probably going to be between, this plus 9% or minus 9%. It's likely what it's going to be. Okay, let's keep moving. Number 8, determine if the sampling distribution for p hat is approximately normal. Oh, this is just the large counts condition for a proportion, which says that it will be approximately normal if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. So that's going to be 15 times 0.17, and that's going to be 15 times 0.83. Okay, so I'll let you guys do the math here. It turns out that, why do I sound Canadian? It turns out that this one here is equal to 2.55, which is no bueno, so we can stop there, and we don't even really need to do this calculation. N times p is equal to 2.55, which is less than 10. So what we can say here is, so we cannot use a normal distribution with a sample size of 15. So what we can do is we can kind of do the calculation and say, all right, well, what sample size do I need for 0.17? Because that's going to be the limiting factor. When you multiply these two together, you think you do get bigger than 10. So it's not a problem. It's this one that's the problem. So you say n times 0.17 needs to be greater than or equal to 10. If you divide by 0.17, you'll get n is greater than or equal to 58.82. Okay? So we would need a sample size of at least 59 individuals to approximate a normal distribution. Okay? Yep. So that one's pretty straightforward, I think. Keep cruising. Number 9, if appropriate, use a normal distribution to calculate the probabilities involving p hat. Well, this one's okay. This one, we have 158 people in our survey. It's saying if 17% of people in Alaska, if 17% of the people in Alaska drink milk, prefer skim milk, what are the chances that random sample of 158 people in Alaska will be between 13 and 16%? Okay, so we can use a normal distribution here because our sample size is large enough. So what we're able to say, so we can say since this is bigger than 59, we've already done our check, we're in good shape. We can say, let's go ahead and get started. We're trying to find the probability, or rather, let's say what our random variable is called. So we'll say let x be the proportion of skim milk drinkers from our sample of 158 Alaskans. Okay, so I think that's kind of what I said last time. Oh, I guess I didn't really do that. That's okay. We're also going to need to know in order to do this, we need to know what we can expect our standard deviation of our sampling distribution to be, because it's not going to be the same as what we calculated here, because here we only had 15, and we know that as that number increases, that's going to change. Lewis, come here, bud. Come here and warm my toes. Okay? So we're going to do the standard deviation of p hat is equal to the square root of 0.17 times 0.83 divided by 158. Whoops. All right, which ends up being about 0.03. So now we can proceed, and we're trying to find the probability that p hat, or rather, yeah, I guess we could just say p hat there. We don't have to create a random variable, but whatever. We're trying to find the probability that p hat is between 0.13 and 0.16. Well, that's going to be equal to the probability that, I'm going to make this a little larger if you don't mind, so writing is easier. That's going to be equal to the probability that, and now we can do the kind of the statistics, the test statistic here. We subtract the mean of 0.17. We know that that's true, divided by the standard deviation of 0.03 is going to be less than, so we can now use a normal distribution, our standardized normal distribution. 0.13, oh no, that's 1. 0.16 minus 0.17 divided by 0.03. So we take our values that were of interest and we subtract the true proportion, or the parameter, divide by the standard deviation. Okay, so let's keep cruising. So when you boil this all down, you do this minus that divided by the standard deviation. We're trying to find the probability that z is between negative 1.33 and between negative 0.33. So if we're looking at that on the curve, let's take a look. We go negative 1 is right there, 1.33 is probably like right here, 0.33 is probably right there. So we're finding the probability of that area. So in order to do that, we find the probability to the left of this, and then subtract that little tiny probability to the left there. So what we do here is we do the probability that z is less than negative 0.33 minus the probability that z is less than negative 1.33. Okay, so we can go ahead and pull up our tables. If you pull up your standard normal probability table, we're looking for to the left of 0.033, which is 0.3707 minus the probability that is to the left of negative 1.33, negative 1.312 or 0.123.0918. So we will get an overall probability when you subtract those of 0.2789. So basically there's approximately a 27.9% chance of the percentages. I didn't write that very clearly, but for our sample proportion to be between 13% and 16%. Okay, let's keep cruising. Number 10, calculate the mean and standard deviation of the sampling distribution of the mean x bar and interpret the standard deviation. Okay. Men's Division I college, Men's Division I college 5K running times has a mean of 970 seconds and a standard deviation of 30 seconds. Find the mean and standard deviation of the sampling distribution of a sample of size 40. So if we're looking at all samples of size 40, we're looking at all possible means, and we know that the center of that distribution of all the means of sample size 40 from our population is going to be centered on 970 because the mean is an unbiased estimator. Okay, and then the standard deviation of all of our sample means is equal to the standard deviation divided by the square root of the sample size. So standard deviation of x bar is going to be, I think it boils down to like pretty small, 4.743. Yeah, 30 divided by the square root of 40 is 4.743-ish. Okay, so that was easy, pretty straightforward. We're going to be using this information shortly. Number 11 says, explain how the shape of the sampling distribution of x bar is affected by the shape of the population distribution and the sample size. I guess we could have talked about this earlier. That would have made more sense with the variability thing. But basically, so right here, notice that I did not tell you the shape of the distribution, right? I said we're sampling from all 5-kilometer running times for Division I college athletes. We don't know what that the population distribution looks like. So we can't just jump into normal calculations for individuals from the population. But you'll notice that if the population looks like this and we're taking random samples, when n is, we already know that as n increases, the variability decreases, but it also turns out that as n increases, the variable decreases and the shape slowly approaches the normal distribution. And so what the central limit theorem says is it says that when we are sample randomly and independently from a population as n gets large, the sampling distribution of the sample mean becomes approximately normal. So the larger n gets, the closer this distribution becomes to a normal distribution, and the smaller the standard deviation of our sample means becomes. Okay? So basically, we can do normal, even if we don't know the shape of the distribution, we can do calculations as if our sample mean is normal if we have a large enough sample size. And for the sake of this course, we'll be using n equals 30. If you have a sample size larger than 30, you can do calculations with the means, not with individuals. So let's take a look at this question. What is the probability that a randomly selected runner is faster than 930 seconds? Well, that's what I'm saying. We can't find this with the information given because we don't know the shape of the population distribution. We don't know the shape of the population distribution, so we cannot do calculations for individual runners. If we had said that it was normal, we'd be fine, but we don't know that. All I gave you is the mean and the standard deviation. What is the probability that a randomly selected, what is the probability that a random sample of 40 runners results in an average time less than 930 seconds? We're fine. Here we are okay. And we are okay because, sorry guys, we are okay because we have a sample size that is larger than 30. So we can go ahead and proceed. And so we can say, what's the probability, basically, that x bar is going to be less than 930 seconds? Okay, well, the probability that x bar is going to be less than 930 seconds is equal to the probability that z is less than 930 minus 970 divided by the standard deviation, Well, that was for sample size 40, which is what we found, 4.743. Let me pull up the correct sheet here. All right. And when we boil that down, it's really the probability that Z is less than negative 8.43. Okay, let's look at our sheet here. Oh wait, the chart only goes to negative 3.4, which means that negative 8 is going to be very, very small. If you wanted to figure out what the actual probability that Z would be less than negative 8.43 standard deviations away, then you would probably need to use normal CDF here. So I would do normal CDF. It's going to be a very, very small number with lower equal to negative 1,000. Upper is equal to negative 8.43. Your mean is equal to 0, and your standard deviation is equal to 1 for the standard normal distribution. If you didn't use the standard normal distribution, you could use this, and it would do that math for you. So you'd say lower is negative, 10,000, upper is 930, mean is 970, standard deviation was 30, and it would do all the math for you. But you need to specify what you're using. Yeah, so we can do that. But basically, this probability is going to be approximately 0. So it would be almost impossible if the true mean is 970 for a sample of 40 runners and the standard deviation given for us to observe something like that. Okay, based on the claimed mean from the previous slide, or previous slide 10, I should say, if you found a random sample of 40 runners that exhibited, so let's say we actually did find that, that exhibited a sample mean of 930 seconds, is this convincing evidence that the population average might be less than claimed? Yeah. Yes, absolutely. It would be convincing evidence. It's going to be convincing evidence because the likelihood of observing a sample mean of 930 when population mean is 970 and standard deviation is 30. So the likelihood of observing a sample mean of 930 when the population mean is 970 and the standard deviation is 30 is very small. I should say by random chance. It is very small unless the population is something less. In that case, what we observed isn't as rare. Okay, that basically covers everything from sampling distributions. We're going to get, I think I'm going to shoot for 2 more videos, one on confidence intervals, one on hypothesis tests. We're going to cover all the different kinds of confidence intervals and all the different kinds of hypothesis tests that you can make, and we're going to look at identifying which different tests to use and which different tests to do. So guys, thanks for tuning into the video. It's been a lot of fun, and yeah, we'll see you on the next one.